Hey everybody, it's Obi-Wan Pez for Nzimblik Spachenko, and we are going to be doing some mathy stuff tonight. So, going to be looking at cracking the GRE, and actually we'll leave that. So last night we were talking about Taylor polynomials and Taylor series, try to approximate functions and find good approximations for those particular values. And what we saw did I go 10 terms? Looks like we only went 4. Hmm. Hmm. Oh, okay. But yeah, we did it on the calculator to get... Okay, never mind. Okay. Hope y'all are having a good night. This is kind of the last page of this particular section. So, just as a little... Hello, Singular Moduli. How's it going? Good evening and welcome. My name's Obi-Wan Pez. This is Nzimblik Spachenko. We do mathy stuff on Mondays and Wednesdays, and gamey stuff on Tuesdays and Fridays, with some asterisks on other days. If you have any particular questions about mathematics education or specifically cracking the GRE, feel free to ask any questions. But all topics are welcome, so feel free to ask about just about anything. Well, it's a Zach. Everybody say hi to E to the 2I Pi. This is Zach. He is another member of our math community and coming on over from his stream. So, Zach, what were you working on tonight? I saw about 10 seconds of it as I was trying to do some other stuff. Alright, let's see. More things that you can remember. That is perfectly fair. Right, so an nth degree Taylor polynomial is going to look something like f of 0. This is a particular one that we were looking at with f of x equals root, wait, oh, e to the x. Of course it would be. Lagrange estimates. Nice. Okay, plus dot dot dot. We're going to take the kth. Well, actually, it would be n, right? Because we're talking about just the last position that we're using. Nth derivative of f at x over n factorial times x to the n. Okay, so our nth degree Taylor polynomial looks like this. Excuse me. No, not at x, at 0, because we have to stay consistent. All right, so how good is this estimate going to be? There is a particular value that we can find. So what's going to happen is we're going to find a particular value. Thank you so much for the follow. Welcome on in. Just so everybody knows, we have a thriving math community here on Twitch. These are the rest of like the fairly large group of people. I believe we're actually missing a couple, but you know, we're getting there. We have Slim from Academy of Useless Ideas, Dr. Gold from Actual Education, Don Factorial, E.N. Stuckey, Zach, you know, from E to the 2i Pi, Meriwether Remark, Penn Center, PhoboStream, Physics and Depression, Talos Teaches, and the Tutor Wizard. We also have a group of friends who like to do study streams, and they do all sorts of topics, whatever they feel like on that particular day. Rendeo, Math Spellbook, Fizzbuzz, Suna Ao, and Walking Stick Library. So they like learning and invite you over too. We also have Math Pond, who is Matt. Thank you so much for the follow. Yes, there we go. Unless it's supposed to be underscore. We'll figure it out. Mathman, Mathman, Mathman. Yes. Anybody who knows... Anybody who knows Square One TV, if you know, you know. And those of you who don't, I suggest looking up Square One TV. It was a PBS show way back when in the 1980s, maybe even 79 or something like that. Creeped into the 90s, and it taught me, as well as many other people, some... If not the explicit math, there was like the idea behind all of the math, and how to do math, not just calculations, but again, like just mathematical thinking. So it was really awesome. If you go onto YouTube, obviously if you just search Square One TV, it's going to give you a bunch. There's a guy named, or, you know, by the name, screen name of Anton Spivak, who tried to, like, digitize his entire VHS collection. So, he's got a good bunch. He does not have all of them, but he's got a bunch. And there's a bunch more that do all sorts of other stuff. So typically the format of the show was 15 minutes toward a variety show, which was like a bunch of game shows, music videos, skits, sketches, things like that, which were just kind of put on by the cast. And typically they were mostly actors. I believe there were one or two actual, like, sort of mathy people. And then they had the last 15 minutes set aside for MathNet, which was a spoof on Dragnet, the old detective show. And those of you who know, goodness, Beverly Leach and whoever played Pat. I have lost her name. Uh, two ladies who played the I actually filled out an application for Where on the World is Carmen Sandiego. They'd never called me back. But I did win my school's National Geography bee for, I think, a 1 for 2 years out of the 3 that I was eligible. And the first time I did not pass the test. The second time in 6th grade, I passed the test, made it to Keene State College, where I got out in the first round. And I'm like, I'm so glad I came. But I did get to see Alex Trebek from like way, way far away. I was up in the balcony, and he was on stage. So that was really cool. Especially since I watched Jeopardy like every day since I was about 4. So yeah, the two ladies of the show who were in partitioned segments. Beverly Leach was the first one. Kate Monday and Pat Tuesday. I cannot remember her name. Why does 1 times 1 equal 2? Yeah, not so much, DCI Banks. Unless you have a different definition of that particular symbol. Which, if that's part of your particular axiom, then absolutely. You can have it be that. So yeah, the two women on the show were the two women on the show were playing the straight man in the group, and Joe Howard, who's like, if you saw him even for a second, you'd know who I was talking about. Joe Howard played the kind of goofy George Frankly, and got away with a lot of stuff, so it was kind of fun. But they go on an adventure every week, and have all 5 days to solve the crime. So 4 days they'd have little miniature episode sort of things, 15 minutes each, and then on Friday they'd solve the case. I mean, you never know. Okay. So, in terms of Taylor polynomials, what we have is the Taylor polynomial of nth degree. So that starts out at 0th degree, f of 0 over 0 factorial times x to the 0 plus, hey Afru, how you doing? F prime of 0 over 1 factorial times x to the 1st. So what we're doing here is we're summing up f, which is being evaluated with the nth derivative at 0, a particular point. So we say that it's going to be like around this particular point. So we're doing it around f at 0 and every derivative thereof divided by n factorial times x to the n. So this is a power series. If you haven't seen that before, you can check out my last video on Twitch about all this stuff. So the like any particular function can be approximated by a Taylor polynomial, which then Taylor series, if it is infinite in length, it is actually identical. So this is what we're doing. We're taking the kth derivative of your function, evaluating it at that particular point, dividing by k factorial, and multiplying by x to the k. there was a actual proof in here on how it all works, like why we were allowed to do that. Yeah, this one. So we assume that f of x is represented by a power series, and then we can prove it doing all this stuff that we get this particular pattern. I shouldn't say proof. I know. I'm sorry, Zach. And that it's going to work for any particular function. Okay. So now we want to know, how good is this estimate actually? So if we have an nth degree polynomial, it is going to stop at a certain finite number of terms. So if it stops at a finite number of terms, then the difference between f of x, which is going to be equal to the full Taylor series, right, we'll still do it at 0, just because of what we're doing here. K factorial, k goes from 0 to infinity, and then x to the k. It's Math Pond! Hey Matt, how you doing? Good evening and welcome. And then we subtract off the p sub n nth degree Taylor polynomial that we found here. Then, like, technically what we get, right, is that we have the n plus 1th derivative at 0 over n plus 1 parentheses factorial times x to the n plus 1 plus f at n plus 2th derivative evaluated at 0 over n plus 2 factorial. And then this pattern is going to keep on forever. So, oh, no, sorry, missed one. Times the term x to the n plus 2. Right? So this goes on forever and ever and ever and ever. And we could also look at this and say, okay, look, if we selected for, rather than 0, if our, like, c value that we're plugging in to f at c and f prime at c and f double prime at c, etc., were instead f at x minus p n at x taken at c equals just like some x value, any particular x value, then we would have the n plus 1th derivative at x over n plus 1 factorial times x to the n plus 1 plus same thing here. Whoop. Okay, so then how good is this estimate? Well, if we have a remainder. Hey Rex, how's it going? Tachyon, thank you very much for the follow. Good evening and welcome. Yes, Taylor Polynomials. Right, so we have these two remainders that are going to be at, let's say, x equals 0, which is where we centered the function. and then x equals just, x, where we're saying like this could be the generic value that we're just going to use. So plugging in any particular x value for these, then we could say that, okay, look, this 0 value that we got here is basically going to be like the lowest particular value that we're going to get for this particular function. And, it goes on and on and on forever, but and then the remainder that we get when x is a generic value, so any particular value that we want to talk about, is going to be like fairly similar, but that could be like kind of a maximum to this particular error. Then what we can do is we could say, okay, look, the actual error that we're going to get, f at x minus p sub n at x for c equals 0. Did I put x equals up here? I did. Change that. Around c equals 0, because again, this is going to be the summation as our k goes from 0 to infinity of the kth derivative at c over k factorial times x to the k. Right, as the generic version of this. So, if our c is equal to 0, then one of the things that we could say is that we end up with the incurred error of n plus 1th derivative of f at some particular... I shouldn't use c, should I? That's what they use in the book, but let's call it some particular a. Right there. Let's go one further, back it off, and say there exists some a in the reals such that the difference between the actual value f of x and our polynomial approximation p sub n at x is going to be exactly equal to the n plus 1th derivative of f at some a value in the real numbers. And I'll put a caveat on that. Over m plus 1 factorial times x to the n plus 1, where our a is particularly between, equal to, or just strictly? They say strictly. Between 0 and that x value that we're looking for. So earlier, we were looking at what would happen if we wanted to find the square root of e. Right? We already know that the value approximated to 9 decimal places found in 10 terms of the Taylor polynomial is going to be 1.6487212171. When we did this as 4 terms, then we found that its value was 1.64583 with the 3 repeated on forever. So, we could come over here and say, okay, our error, so e to the 1/2 was going to be approximated by let's go there. 1 point. It's like terrible. I should know better. 1.64583. Right? Just keep it down to that many decimal places. We'll call it, right, these 5 decimal places here. Okay. Then with it being this is a polynomial 4 at 1/2 is going to be e to the 1/2. Shoot, hang on. Let's rearrange it. I got to be careful how I say things. You all know how it goes. All you teachers out there. Everything's too literal. All right, e to the 1/2 is approximately p of 4 at 1/2, which is okay. We'll put that in. There we go. It was whatever. It was approximately that anyway. I'm just going to argue with myself for a while. It's fine. So p sub 4 at 1/2 is this value, 1.64583 repeated. And again, it's close enough for a 4th degree polynomial to get e to the 1/2, right? Our square root of e, which again, we know to the correct 9 decimal places, 1.6487212. So 1.645 instead of 1.6487. So if you squint, it sort of looks almost right. So here we want to know what's the error. Right, now you could do your standard percent error that you do in high school, middle school, that sort of stuff. So we get if we want to do percent error, say we want to do 100 times actual minus experimental over actual. And that's absolute value. Just to make sure it doesn't turn negative. Okay, and this is going to be approximately there. That one. Store to E, experimental. And that one, store to A, actual. Okay, so now we want the absolute value of A minus E over A times 100. That's gross. It's actually not that bad. Is approximately 0.175%. Okay, so if we wanted percent error, that's what we got. Again, actual difference between them, right, would be the absolute error, which is just going to be A minus E, absolute valued. Which is about 0.0028879, but, close enough. Okay, and then we can go with the Exact error calculated by Taylor. So what we're going to do is we're going to take e to the x. Let's move that over just a little bit. And we're going to take the, nope, we already have the 4th degree polynomial, so we're going to take the 5th derivative with respect to x of e to the x and evaluate it at, in this case, x equals 0, same place that we did before. Nope, I'm sorry, that's c. We have to find c. Sorry, I haven't done this in this particular thing in a very long time. We divide it by 5 factorial. And then multiply by x to the 5th, where x in this case is the 1/2 that we had up there. Hey Famished, how's it going? Okay. So here what we've got is e to the c over, nope, not 2 to the 5th. This is 5 factorial, which is going to be 120 times 1/2 to the 5th, that's where that came from, is going to be 1 over 32. And we said that c needs to be between 0 and 1/2. So then e to the c, because e to the x is a 1-to-1 function, we can just utilize e to the 0, which is 1. Right. Next question, where do they go with this? Let's see. So this thing here, 120 times 32, got 0, 2 times 0 is 4, 1 times 2 plus 2 times 3 is going to be 8, and 3 times 1 is 3. So 3840. Anybody not seen Vedic multiplication? Right, it looks an awful lot like, regular multiplication, but what we're doing here is we'd say what makes the ones, in this case it's 0 times 2, which is 0. Tens is going to be 2 times 2 plus 0 times 3. Ones times tens, sorry, tens times ones plus ones times tens, which is 4. Hundreds. What makes the hundreds is going to be hundreds times ones. So we've got a 0 times 0. We've got a 2 times 3, tens times tens. And then we've got a ones times hundreds, or hundreds times ones, 1 times 2. This is going to be 6, and 2 make 8, and then 1,000. Tens times hundreds, or ones times thousands. So here we've got a bunch of 0 times zeros. We've also got the tens times hundreds, hundreds times tens, 1 times 3. Right, so that's going to be 3. And then here we're just reading it upward. Right, 3840. So Vedic multiplication is actually like printed into the Hindu Vedas because they thought it was important enough that people in the future should, at the very least, learn it from the Veda. At the very least, it would be backed up in there somewhere. Okay. So what we've got is 3840 be e to the c over 3840. Let me just check something. I'm going to take out this word here. Right, so the Taylor error, we're going to say that error Taylor is going to be less than this amount here. Okay. What did they do? Ugh. Okay. All right. That's what they did. Okay, so it wasn't all this complicated nonsense. Right, we have a value e to the c over 3840. And basically the idea is, okay, what we want to do is to find e to the c, maybe with this 3840 tagged onto it or whatever, such that we can find a reasonable approximation for this thing. So, they chose asterisk, right, that E is equal to this 2.718281828, whatever, is less than 4. I think we can all agree. So therefore, this is going to be less than 4 to the 1/2. So this is a wild amount of error, but nonetheless, we're just choosing it to say, okay, look, this is less than 2. This e to the c. And we already know it's greater than 1. So what we can do is say, look, the error is going to be less than the amount that we have here, because what we're going to do is we're going to assume that e to the c is just going to be 2. So our Taylor error is going to be less than 2 over 3840, which is 1 out of 1920. So we have to make a little bit of an argument for it, but this is the idea. We can find some value that is going to bound our error on above what we have. Trying to finish up advanced PC applications quickly as you can so you can move on to HTML coding. Nice. I totally forgot something up here too. Should have stopped me. Remember that for Taylor polynomials, this isn't just if we choose some other point A that is not 0, then our Taylor ends up being f evaluated at A, and then we do x minus A as the, we shift our x value. All right, anyway. That's not what I meant, though. Man. Sorry. See, that was the danger of using A as well. Right. Yeah, we'll do another one some other time. So let's reset the canvas and then go to our Chapter 2 review. All right, this is essentially going to be our final exam for like Calc 2 for the GRE. Watch a preacher or like watch a show called Preacher? Show called Preacher, all right. Did didn't know if it was suddenly being like, you need to watch Joel Osteen. All right, number 1. Consider the sequence x sub n whose terms are given by the formula x sub n is equal to cosine of n pi times sine squared n over the eth root of n. All right, for n greater than or equal to 1, and also n being positive integers. I guess that's kind of redundant, right? If it's positive integers, then it is already greater than or equal to 1. There's actually a really good documentary. It's not really a documentary. Good show that was done by Darren Brown, who is a he hates the term, but psychological illusionist. I think he goes by the term mentalist just because it kind of harkens back to the old days where people would do a stage show and they'd mess with your head. So Darren Brown, Derren, did a show called Miracles for Sale, and it got a lot of flack from people who didn't watch it, because he is quite openly a gay atheist. And like at one point in one of his shows, he got a guy to like call his father, and then he would tell him on the phone exactly what the dad was thinking. But he had just asked the son like all sorts of stuff about his dad. And he says, "I swear to God and on the life of my children." Oh dear. But in Miracles for Sale, that kind of bothered people. But in Miracles for Sale specifically, he was not doing like a bad thing and just like, I'm going to make fun of religion. It was specifically, he got help doing an investigation from a number of people who live in America and like still go to a church, still believe whatever they believe within their subset of Christianity, but their relative was taken in by a sham miracle worker who told them that they need to spend all of their money, they need to give it all to the church, all this stuff. Kills it out, yes. We can do some Calc 3 as well. If you are at all interested, let me know what you would like to do, and I will put it on the list. But they were basically told, give all your money to the church, and miracles will come to you. And then when the miracle didn't come, because it doesn't work like that, they said that, well, she must not have been faithful enough. And there have been a number of cases of people pulling this all across America. The most egregious of which was a young lady who ended her own life because of this. So he worked with that family, like their relative is still alive. He worked with this particular family to be like, okay, look, we need to do something to go against this like hypervangelism, which is trying to drain people's money, and like that's all they're doing. And so he made a whole show about it. Got a guy that was like part of a competition at the beginning to see who was like the most charismatic speaker, and got him to dress up as a evangelical preacher. And again, not all evangelicals, just this particular sect that was like, money, money, money. Everything's about the money. Got him to like infiltrate the sect and give a speech at the end of it to give them something to chew on. It's quite interesting. Differential equations, specifically with... would you like differential equations specifically with multivariate hooked in? And then which part? I do not have a Discord. However, we do belong to a larger group. Posted this a little bit ago. These are all of the other, well, not all, but these are many of the other math friends that we have. And I will get you a Discord to the one that we, like, a lot of us hang out at. It's called The Elements. And this server is... belongs to Penn Center, so you can see his name there. Most of the rest of us hang out there for some amount of time, so you can come and find us there. If you would like to post one now, then you could post one either in the Maths forum or the Maths chat, and we can work on that. Otherwise, I can come up with some stuff. Nonlinear Euler Cauchy. Whoa. Okay. Could probably find something. Cauchy-Euler equations. LibreText. Okay. So for anybody who doesn't know what this is yet, the Cauchy-Euler equations within differential equations are of the form a x squared y double prime plus b x y prime plus c y equals 0, where right, y is a function of x, y equals y of x. That'll make it easier to deal with. The one that gives you series. Yeah. Okay. So because of that, I better find one that actually works nicely, or sort of nicely. Okay. Okay. So, for instance, t squared y double prime plus 3t y prime plus y equals 0. Initial condition, y of 1 equals 0, y prime of 1 equals 1. Yes-ish. So differential equations is one of my specialties, I guess. I am sometimes a little rusty just because I don't do it all the time, but it is what I dived into more in depth for my master's program. So I did both nonlinear and partial differential equations. Like I said, it's been about 15 years, but we've been doing some here and there, so they're kind of fun. Okay, so we assume that y is of the form, right, a sub k x to the k, where k goes from 0 to infinity. So therefore, y prime is going to be equal to, now this is where it gets fun. Here, what's going to happen is we're going to get the k to come down front. This is still a sub k, doesn't change anything. Multiplied by x to the k minus 1. So we take the derivative with respect to x. Right? This is going to be dy dx. Okay, now here, if we plug in x equals 0, or sorry, k equals 0, then we end up having a bit of a problem. Let me pause this for 5 minutes, and then we'll do an ad in about 6 or 7 minutes. So we'll be able to get some stuff out of here. If we end up plugging in k equals 0, notice what happens, right? Like, the whole thing is just 0. So it's pointless to use k equals 0, so we just tick up and go let k equal 1 and go from 1 to infinity. All right, similarly, if we take a second derivative, then we're going to get, again here, we're going to get a k minus 1 and a k times a sub k times x to the k minus 2. And again, k equals 0 and k equals 1 are both zeros of that polynomial now. So now we just say, okay, well, let's start with 2 so that it's not going to be 0 anywhere. Open stacks, yes. Yeah, so it has algebra books for all of those sections. You could go for college algebra. I would probably suggest starting with maybe Algebra 2, or they probably have a couple others that are in that area. I'm not sure exactly, just because I'm going to put this down because I don't need it right now. We're doing something completely different. Okay, so with this, what we're going to do... Oh, those are X's. Curses. Right, so we're going to bump these out and say these are T's rather than X's. I do this all the time. Drives my students nuts. What we're going to do is plug in those series in for y prime, and y double prime. So this is going to be t squared. Y double prime is the sum from k equals 2 to infinity of k minus 1 k a sub k times t to the k minus 2 plus 3t times the sum, as k goes from 1 to infinity, of k a sub k t to the k minus 1 plus y, which is just the sum of a sub k times t to the k. K goes from 0 to infinity. That is all equal to 0 with the above conditions. Okay, now we just look at this and we say, hey, guess what? We got these nice t terms that are sitting out front of these terms which have fewer t's than we would kind of like. So there's kind of two ways to deal with this. One is that you math is powerful. Yeah, that's a good one too. I haven't fully vetted it, but I've poked around a couple of times. So there are two ways to deal with this. One is that you bring in the t's because they're not a variable in terms of the summation, right? If you have a t that's multiplied on the outside of a bunch of sums, then you're just multiplying it to each one of those things. And so therefore we could just multiply our t squared onto this. So this is actually not terribly bad. So we still have k going from 2 to infinity of k minus 1, k, a sub k, 2 more minutes, times t to the t squared times t to the k minus 2 is just t to the k. Right? Sum. We're going to bring in the 3 and the t. Summation. K goes from 1 to infinity of k a sub k times t to the k minus 1 times t is going to now just be t to the k times 3. So we need that 3 in there somewhere too. Okay, plus summation. K goes from 0 to infinity of a sub k t to the k. And then all that sum is equal to 0. Now, we are not allowed to combine these. Right, so this is fix exponents. So this is option 1. Option 1 is fix the exponents. You can't sum these because our k values are not the same. So one of the things that we can do is, I kind of liken this to ablation. So we kind of burn off the extra terms. So we've got this k minus 1 times k times a sub k times t to the k plus, this has an extra term at k equals 1. So let's plug in k equals 1 and get stuff here. So when k equals 1, we get a 3 times 1 times a sub k is 1 times t to the k is 1. So 3a sub 1 times t plus summation as k goes from 2 to infinity of the same thing that we had above. 3k times a sub k times t to the k. Okay, plus k equals 0 now has k equals 0 and k equals 1, which don't match, all the rest of that stuff. So we ablate those off. So a sub 0 times t to the 0, which is just 1, plus a sub 1 times t to the 1, plus. K goes from 2 to infinity. Adds are about to start here. Sorry. A sub k, t to the k is equal to 0. Okay. With that, we'll be right back. So see if you can chew on this a little bit. Maybe also work on it just for a couple minutes while I'm out. There it is. All right, 3 minutes. Be right back. Thanks for coming, everybody. All right, welcome back. Let's also do our fitness stuff real fast here so we can get back to it. So, yeah, that one's quick. As long as I don't, like, get a heart attack and drop dead, I'm fine. All right. And 1, 2, 3, 4, 5. 7, 11, 12, 14, 15, 16, 17, 18, 19, 1, 2, 3, 4. Woo. Right, 30 in a row, probably the most I've ever done. Right. So, let's just double check that real quick. So, or you did that, right? Yes. Okay. Thank you. All right. So usually I like to match up stuff first and then right, we'll ablate these extra terms, get them off, and then we'll be able to combine all of these things. So this is going to get us summation. K goes from 2 to infinity of k minus 1 times k, a sub k times, oh, no, hang on. We'll take all this together. So all of the ones that have a t to the k just all come together. And actually, a sub k, right? It's also going to come with us. So we have a k minus 1 times k times a sub k t to the k. Then we also have a plus 3k a sub k t to the k. And then we have a plus a sub k t to the k, which is just 1 here. All right, a sub k t to the k. All right, then we have the spare terms which dropped out. So we have a 3 plus 1 is going to be 4, a sub 1t plus a sub 0 is equal to 0. Right, this is what the whole system has now become. Right, so for right, for y at 1, we're not there yet. It'll be fine. We got a sub 0. We got 4 a sub 1t. Then we've got next term, we plug in k equals 2 to all that stuff there. We could also simplify a little bit here because we have a k minus 1 times k. So k squared minus k. And then that minus k and the plus 3k can combine. So we can make this k squared minus k plus 3k plus 1, so plus 2k. Alternatively, k plus 1 squared could also work if you feel like it. We plug in k equals 2, right? Yeah, actually. K plus 1 parentheses squared. When k equals 2, we add 1 and we square it, we get 9. And when k is 2, this is a2 and t squared. Plus, and then all we're doing now is we're going up a square. We're increasing our subscript and our exponent at the same time. So 16 a sub 3t cubed plus 25 a sub 4t to the fourth plus, and then that is going to continue going on and on forever. So yeah, if we just take this and plug in we have to plug in 1 for t. That's not very kind. Yeah, no, that's true. Maybe I just confused myself. Sorry. Yeah, we already know that this is going to be k plus 1 squared a sub k t to the k. And it actually did hold for the other two, right? There should be two separate patterns, though. I just got myself stuck. What happened? It is likely the case. But, but we don't have any information on a sub. You meant a sub. Okay. Right. God, what is the matter with me? Okay. Oh. Ooh, we could use Taylor Polynomial. That's gross. Kind of like it, though. Yeah, maybe not. Okay, this... Do we have y, though? So that's a sub k t to the k. A sub k t to the k. Right, okay. So this is y. This is y, but just times this other stuff. Oh, man. Right, this is equal to... the summation of that, but no, because you can't multiply by a term that's already in there. Oh, gross. Right, you can't separate them out. Grr. Okay, very odd looking at the end. So if it's equal to 0. So I don't think that this one is very compatible with using the series solution, which is terrible. I'm sorry. So I think I maybe should have done a different one with that. See, this is why when you do things like this, you really got to make sure that it's meant for the thing that you wanted it to be meant for. All right, so contents. Numerical solutions. There we go. Whole chapter on it. And nope, nonlinear systems. The other one. Series solutions. Hey, there we go. There's a different Cauchy-Euler situation. Makes much more sense. That's gross. Why'd you do that? Woo. Okay. Let's try this one first. And then we'll do power series on that one. On the previous one. This is x squared y double prime minus x times 1 minus x. Much better. Y prime plus y equals 0, not random factorial. Okay, so we want to let y equals summation a sub k x to the k. Again, k goes from 0 to infinity. Y prime is equal to, honestly, I should just copy paste this part. K equals 1 to infinity, a sub, nope, k, a sub k, x to the k minus 1. Y double prime is equal to summation k goes from 2 to infinity. K minus 1 times k times a sub k times x to the k minus 2. Okay. So this is x squared times the summation k goes from 2 to infinity of k minus 1 k a sub k x to the k minus 2 minus x times 1 minus x times the summation as k goes from 1 to infinity of k times a sub k times x to the k minus 1 plus y a sub k x to the k inside of a summation in the first place. It goes from 0 to infinity. So again, kind of two options on this. One is to bring in the terms, match the exponents, and then, again, ablate any of the extra terms. In this particular case, we do have an x squared that's attached to the x to the k minus 1 term. So in this particular case, we will get mixed powers, which this will work. Okay, so that is something that is going to work on this one. Because they're the same power. So you couldn't, like, match this this particular equation with this particular equation over here, which have the same power. So we want differential treatment of powers within the same expression. Right? In this one, unfortunately, it turned out that, oh, hey, they're all the same expression. So, like, if you just plug in t equals 1, then nothing really happens. Like, we just get a whole bunch of stuff. And again, this is not y, which is the other problem with it, right? This is not y. This is what happens when you plug in all of this stuff. Right, and we don't have a value for y double prime at 1. So, like, I mean, why would you need one? So in this particular case, you wouldn't come up with anything in particular. You're just kind of stuck. I guess in theory, right, you could just take y and y prime and plug in the single stuff. No, it doesn't really work that way. But anyway, yeah, you need differential treatment of powers in order to make this work. Anyway, Laplace might be simpler on that one, so we can try that next. So for here, we end up with, again, k is 2 to infinity, k minus 1, k, a sub k, x to the k. Okay, then this one is going to be a minus x plus x squared. Okay, let's make that a plus plus x squared minus x, right, times the summation, k goes from 1 to infinity, k, a sub k, x to the k minus 1. Hasn't done anything just yet. Okay, plus summation write k0 to infinity a sub k x to the k equals 0. So here, again, we need to ablate some terms. So we get the 0. Or no, I'm sorry. This one's going to stay where it is. So k goes from 2 to infinity of k minus 1 k a sub k x to the k plus here we have x squared minus x times, if k is equal to 1, then we get 1 a sub 1 and x to the 0. So just that. Then we get, nope, x squared minus x times the summation. K goes from 2 to infinity of k a sub k x to the k minus 1. Yeah. Plus, if k is 0, we get a sub 0. And if k is 1, we get a sub 1x. Plus, k goes from 2 to infinity, sum of a sub k x to the k. Ugh. Equals 0. Right. So now we get this stuff. We end up with summation k goes from 2 to infinity. Okay. Anyway. Okay. K minus 1, k, and a sub k. It's fine. We'll wait on that. You know what? Hang on. So let's do a sub k x to the k times the quantity, all of the things that'll be there. So this is going to be k minus 1 times k. Next one over is going to have a sub k times x to the k when the x comes in. So that's going to be a negative k a sub k. No, a sub k is already gone, right? It's out front. Okay, so x, the negative x, times k a sub k x to the k minus 1 ends up becoming a sub k x to the k times negative k. So we just get this negative k dropped in right here. Okay, then we also have the plus x squared. So this is going to lead us to have a k and an extra x. So where'd that come from? Now, this one's okay. Okay. So this is going to work out all right. Because we have the extra x in here, we're going to now have this possibility for differential treatment between the two pieces. Okay, and then a sub k x to the k is just 1 at the end. Then then we have the extra pieces that are laying around. So we have an a sub 0, we have an a sub 1 multiplied by both an x and also a negative x and also an x squared. So this stuff is gone. That leaves us with an x squared times a sub 1. So now this is all equal to 0. Okay, so 0 is equal to a sub 0 plus a sub 1 x squared plus, if we plug in k equals 2 into the sum, then we end up with a sub 2 x squared. Should probably simplify that. Yeah, it's fine. This is going to be k squared minus 2k plus k, and let's go 1 first, plus 1 plus kx. Okay, so this is a sub 2 times x squared times, the constants are going to be k equals 2, so this is going to be, we could also make this again, k minus 1 squared for this part. So 2 minus 1 is 1, squared is 1, plus a sub 2x squared times k, which is 2, times another x. So this is going to have an exponent of x cubed on this stuff right here. Then, when we go to k equals 3, okay, this stuff here is k equals 2. Plus, right, evaluated where k equals 3, we end up with this next group. A sub 3 x cubed times 3 minus 1 is 2, squared is 4, plus a sub 3 x cubed times the quantity. This is now 3x. Plus, when k equals 4, we have a sub 4 x to the 4 times 4 minus 1 is 3, squared is 9, plus a sub 4 x to the 4 times the quantity. This is 4x. Okay, and then that means that we're going to be adding terms this way. And these two. Okay, so here's the exciting part. Now we can equate something with an A2 and something with an A1. Something with an A3 to something with an A2. That's where we get the, oh, hey, this works thing. So, in order to get 0, all term coefficients must sum to 0. Okay, which means a sub 0 has an x to the 0 attached to it. There's nothing else there. So a sub 0 must be 0. Now, we can maybe go back and look at the other one and do the same, but I think all of them end up being 0, so it doesn't help. Okay, so a sub 0 is going to be equal to 0. Then, when x is equal to 1, nope, not doing that yet. Okay, in x squared, this is x to the 0, x squared, we have a sub 1 plus a sub 2 must also be equal to 0. So therefore, a2 is negative a1. In x cubed, we have an a4, a3, plus a 2, a2, which must be summed to 0. And since a2 is negative a1, we can move it over to the other side. A sub 3 is going to be equal to, this is negative a1, so negative 2a1, add to the other side is going to be 2a1 over 4, so therefore this is 1/2 a1. Okay, and then, comma, for x to the 4th, we have a 9a4 plus 3a3 is going to be equal to 0. a3 is equal to 1/2 a1. So this is going to be a4 is equal to negative 3/2 a1 divided by 9 times 1/9, which is going to be equal to, this is negative 1/6 a1. X to the 5th. So we could do the same thing here. This is going to increase to 16, and this is going to increase to 5x. This is going to increase to a 5, and this one is, oh, whoops. Right, never mind, that's that way. So with x to the 5th, we have a 16 a sub 5 plus 4 a sub 4 must be equal to 0. Divide both by 4. Move, no, hang on. Make this a negative 1/6 a1. Yeah, it's fine. A sub 5 is then going to be a positive a sub 1 divided by 6 times 4. Looks like it. A sub 0 drops out. Yep. Yep. So it's looking like, at least so far, what we have is then y is going to be equal to a sub 1 x plus minus, I guess. Right? A sub 1 x squared plus 1/2 a sub 1 x cubed minus 1/6 a sub 1 x fourth plus 1/24 a1 x to the fifth plus dot dot dot. A sub 1 times the quantity x minus x squared plus 1/2 x cubed minus 1/6 x to the fourth plus 1/24 x to the fifth minus dot dot dot. I mean, yes, relatively easy, but at the same time. Right, times 1, times 2, times 3, times 4. Oh, factor, yeah, okay. Jeez. Alright, x to the first over 0 factorial minus x to the second over 1 factorial. I was trying to think of numbers that were x to the third that were like, I don't even know. I was trying to think of polynomials maybe. Minus x to the fourth over 3 factorial plus x to the fifth over 4 factorial minus dot dot dot. And then a sub 1 times all that. I do have a slight problem with this, and that being that this is a second order differential equations, so there should be 2 unique solutions. However, I'm pretty sure that this is known. That this one is going to come out with one solution, and then you have to come up with the second solution. It says here, using the method of reduction of order. Yay. Right, so this is only y1, and then the book I'm using says find y2 by reduction of order. Or like just literally another method. So the issue I think is that this is just not the way I was expecting it to go, but it's fine. Anyway, here's the, just put my finger in the cup over there. So that's the differential equations book that I was looking at on LibreText. There's also one on, who's it's? OpenStax that works great. So, why, thank you. I will say, if you go and watch many of the other people, they will struggle less. Mostly probably just because it's been a while since I've done this particular sort of thing. And again, I was looking for something that was going to be nice when we actually worked with it. So if we want to do... oh, no, let's just take the whole thing, right? If we want to do Laplace transform, This is, again, another one that I'm just going to stare at for a little bit. So, you just shake it a little bit and it should clear up. Yep. So we're going to assume that not quite. Okay, so we're going to take the Laplace transform of this whole thing and the Laplace transform of the other side. 0 should just get us 0, unless I just messed everything up. Hang on. Yeah, right. Okay. So we're going to use this table here to just be able to calculate all the quick ones. Let's make sure we get that over there. Okay. So the Laplace operator is a linear operator. So using this, we can go in and say, okay, this is going to be the Laplace transform of t squared y double prime plus the Laplace transform of 3ty prime plus the Laplace transform of y equals, and again, this should be 0. Okay, so the issue with the one that we're trying to do at the moment, we just want to make sure that we're using the appropriate table, or the appropriate entry on the table. It may be slightly easier if we did this. It's fine. Okay, so what we've got is a function times another function. Specifically, t to a k power, or t to the n power, times a derivative. So what we want I swear I had one here. Well, it might be the one that I was using previous semesters, which was a function times a polynomial. but there's a specific reason. So when we're using this, the issue is that the Laplace transform will end up being, like, essentially, because it's an integral, what we're going to be doing is we're going to do integration by parts, and the one side is just going to keep getting knocked down by powers, while the other side is an e. So e to the whatever ends up just staying as it is. It's pretty nice. But let's just make sure. There we go. Laplace transformation of a product is not the product of the transformations. So, we do have to be careful with this. Okay, convolution. Have to use a different type of product. This might have walked into a much harder thing. Like, I swear I did one of these before, so it seems like... Trinity Trench, there we go. And then we get into I can't just go in. All right, I think I have it downloaded already. Math, books, nope. Differential equations. Oh, there it is. Okay. Okay. Here's a direct link to the other book that I have here. This is William Trench. I actually taught out of this book and ran the differential equations course that I did on this channel out of this book. So, all right, introduction. But the thing is, right, I thought that the convolution was actually easy-ish when you had a just polynomial. But maybe not. Oop, there we go. T to the n, e to the at. Oh, okay, no. Because that's not an exponential. mean, they do have like T cinch, but cinch is a exponential. Okay, so in theory, that might be too convoluted. Hey, it's not quite helping what I wanted to do it. Or this isn't what I wanted it to do, but that might be an inverse. Yeah, okay. We used to do constants multiplied by the derivatives. That's why. We didn't, I don't think we did t's multiplied by it at all. Unit step function, yeah. Ugh. All right, hang on. Yeah. Oop. No. Yeah, me too. Or even just like t to the n times f. I was positive that there was one of those on the table, and I can't find it. So it could just be that it's not actually there. Yeah, no. Okay, let's zip down to the part that has the other. Okay, constant coefficient throughout this whole section. Man. Linear, higher order. Okay, ads are about to start. I'm probably gonna do some Tai Chi while we're here. So, anybody wants to hang out and watch that, feel free. Otherwise, I'll see you in 3 minutes Be right back. Thanks so much, everybody, for coming. And thanks so much, Kizzled Out, for supplying some problems here, or the direction. So, see you in 3. All right, for anybody who's back, this is our usual Tai Chi warm-up. So we kind of let the arms fly a little bit, and we just shift our weight back and forth. Try to keep the... I was given a little bit of a correction today, so put the put the weight on the balls of your feet and try not to lift your heels off the floor at all. So we're just kind of do a little bit of quick shifting of weight back and forth, just a little bit. Again, try not to lift any part of your foot off the floor. Keep the weight mostly in the balls of your feet. And just by shifting your weight, you're kind of letting your arms swing as they're going to swing with very minimal input. Just like little things to make sure that you don't do something like this and like jerk on your tendons, because that's not good for them. Be nice to your body. You only got one. Alright, so once we've done swinging on both sides, there's also the Nordic skiing version of this. So we're going to go to switch both sides, or switch sides to go like this. If you can, keep up with the music, but it's usually not the natural period of my body, so... This this warms up your tendons, warms up your muscles, and also gets synovial fluid moving in your joints, so that you're less likely to hurt yourself when you do like martial art type stuff. So, anybody who doesn't know me, my name's Obi-Wan Pez. This is N Simplex Pachinko. We do mathy type stuff on Mondays and Wednesdays. We do gamey type stuff on Tuesdays and Fridays. And then we intersperse, sprinkle in a little bit of martial arts basically anywhere we can, because I'm getting old. We need to be able to do some amount of physical activity, otherwise things get really stiff. Alright, and then we do bear also. So kind of relax, roll the shoulders a little bit forward. Hold your arms out like this, and then we kind of shift into the inguinal crease, which is that like crease that's between your quads and your abdomen, so like right on the groin muscle. Kind of turn in this way, and then we back up toward the opposite side. Kind of grab the ground with your toes a little bit, and then we turn the other way, and then we back up this way. You try not to go beyond, try not to get like your butt further than your calves, because then you can end up hurting yourself somewhat. So if we do this, we can, again, push and pull with your toes and kind of get this bear movement. And then once we're done doing this, we also do another one where we do like a ward off and come to the other side. And then we turn, and then we do a ward off here, come to the other side. I think he called this cloud hands. Hell if I know why. I think that's just what the Malaysian masters that he studied under call it, so therefore it's called cloud hands. You don't want to mess with them. So I've been studying Tai Chi for like, I don't know, less than a year. But I have been doing too much movement. I have been doing Tang Soo Do karate for about 17 years. So so I at least know some of what I'm doing. My instructor says I'm a very quick study, so, you know, yay. Okay, so the Tai Chi form, I have now learned almost a third of it. Start with our toes in a V shape on the ground. And then we kind of pick up the body, start in bear, tuck into the right inguinal crease, and then step left and straighten out your toes. Then from here, we breathe in for 2 and out for 2. Bring your hands up, push out, and then from here we create a little energy ball with our hands right on top, left underneath, and tuck into the, no, where am I going with this? We want to step, man, there we go. Okay, tuck into the left side, create that energy ball, turn on the right heel, and then we step forward here, step left forward, tuck into the inguinal crease again, and this time ward off to the left, turn the heel, and then our right hand stays kind of back. Then we kind of tuck a little bit to the left, turn on the right balls of our feet, and then step out, doing a right ward off, turn on the heels. We do a roll back, which typically is when you're kind of attached forearm to forearm with somebody. They're trying to do something, they're trying to push through you. You just kind of like let them go. So you want to come this way? Sure. Let's come this way. So tuck through a little bit, and then reinforce your hand to push. This is called a press. Break the hands apart, set back, and then actually push. You don't want to shove with your hands, but rather what you do is you set your hands at like a given location, and then you just use your body weight to let that push happen. And right at the end, you can then give it a little extra push to increase the momentum. It's pen center. All right, then we sit back again on the left side, turn on the right heel, come this way, and we make our feet really awkward. And then we go further, tuck down, make like a little miniature energy ball. We're going to pull up on the left heel and let this single whip fly this way at the same time. And all of this energy kind of undoes itself kind of at the same time. Single whip is really nasty, by the way. If you get hit with something like this, that's all of your wrist bones just smacking into something. If it's a person, it's going to hurt them. We step out, bring the arm out like this, and then we are going to turn, shift weight, and turn our foot all at the same time. Come down with our hands, lift hands this way, put 0 weight on our right foot. Hey, Pen, how's it going? All right, and then we bring everything back in a bit, and then we do a shoulder strike. So this is going to run into somebody. Again, my body weight is not insubstantial, so this will collide with somebody, and they will be moved. We then turn the back foot a bit, tuck in on this side, and do what's called white crane. So here, my instructor said that this is actually something that the cranes do in Malaysia. They're trying to like air out their wings a little bit, so they kind of come up and let them sit in the sun for a bit. All right, from here, what we do is we're going to basically do a block this way, and then as we're coming arm across, this hand comes back up next to our head, and then as we step out, this is going to be a strike and a brush parry to move it away from our knee. So from here, we use our body weight to do that at the same time. Then I need more room. So we go from here. We step up where our heels are together, and then we strum the lute. Don't know why that's that. And then we do the brush parry thing again. So we go like that. And turn again in there. Then, this is what we did today, so I got to remember what we're doing. From here, okay, we've just done the second brush parry, and I don't remember a damn thing. Oh yeah, we turn 45 on the front leg. We shift our weight forward and drop the right hand into a fist. Left hand stays together. This comes through, and basically we're going to step 90 degrees, like on somebody. So probably against their leg, slide down, and potentially break an ankle. Not ours. So we're stepping here. Step here. Step through, and we're going to go and pop. Do a quick punch this way. Oftentimes this is, he said, this is going to be like lifting somebody's arm under here and rendering this arm pretty useless for them. So you kind of come up like that and then pop underneath, and especially if you're popping around the floating ribs, that can be some pretty devastating movement. Okay. We'll call that good enough. Hey, Pen, how's it going? Caller, good to see you. Oh, Take the normal Laplace and take the number of derivatives based on n. It's been so long since I messed with that. Because this is... Laplace is... integral from 0 to t of e to the negative s... Is it as? Times f of t dt. Two derivatives on the first term, one on the second. Right, so if we did this, oh no, ds, right. Right, so then with respect to integration by parts, we have to decrease the t. Oh, but it's with respect to s, so... Yeah. Okay. So this is going to be, like you said, the... Well, okay, so the Laplacian of y double prime is going to be s squared y plus... Ah, crap. Yeah, I know that this is a solved problem. I mean, in terms of no, because I got paranoid. This is s. Oi, yeah, it has been way too long. Gray. Here we go. Gray book. Right to the Laplacian. Nice. Yeah, no, okay. So this is y at 1, I guess. Plus y double prime at, or y prime at 1. Minus. Let's minus all those. But right, the issue is having all of those that have t's attached to them. Two derivatives of what, though? Because that's just going to be 2. Or like... Oh, but this is y of s. As in product rule? Might have been the end of our music there. Probably. Start over. Okay, so Laplacian of t squared y double prime is going to be equal to second derivative of s squared y. Y is a function of s. Minus, yeah, minus y. S y of 1 minus y prime of 1. So 2s y, okay, hang on. ds of 2s y plus s squared y, big Y prime, which then is going to become 2y plus 2s y prime plus 2s y prime plus s squared y double prime. Okay, minus s y of 1 minus y prime of 1 s y of 1 minus y prime of 1. That way. Okay, now we got to do it one more time. So L of 3t y prime is going to be equal to 3 times the second derivative with respect to s of 2, no, sorry, first derivative. Wait. Derivative of ty prime. Nope. Boo. T big Y. S. Jeez. Oi. sy. Minus, nope, minus y of 1, which is 3. Three times everything. Oi. You punks. You're not going to give me the Q? It's just going to... Oh my god. So if I go like that, and then, yeah, see, that's what happens when I... There we go. Messed up the product rule. With respect to s, right, we take the derivative of 2sy, we get 2y, plus 2sy prime, plus 2sy prime, plus s squared y double prime. Which part of the product rule? I mean, I could combine those other two, but I was less concerned with that. Nope. Y plus s y prime minus y1. Which part? In that I didn't combine terms? Right, because like those two belong together, but I just didn't do it. All right, we said that y prime at 1 is 1. Oh, okay. And y of 1 is 0. So these are all 0. These are all minus 1. These are all 0. All right. Woo! Y plus 3s y prime. Nah, no worries. All right. Plus in 3t y prime. And again, this is going to be evaluated where y of 1 is 0, y prime of 1 is 1. Okay. So we've got an s squared y minus 1 Whoa, nope, hang on. Oi. That's not what I wanted. Okay, so from here, we got 2y plus 2sy prime. Nope, 4sy prime. Plus s squared y double prime. Minus 1. Plus 3y plus 3s y prime all equal to 0. Nope. Hang on. Oi. Plus y equals 0. Okay. So this is going to combine together to make a 6y. Ugh, right. Let's do the differential equation from the other side, because this is another differential equation. S squared y double prime. I did not alternate. Do you mean there? I mean, if so, that's a quick fix, but nonetheless. Which ones we're supposed to alternate? Section 8. So I've got the stuff with all the initial conditions is supposed to just all be negative, and the Laplacians themselves are supposed to be positive, or whatever sign they came from. Um, that's just t to the n property. Great. So it's not really the product rule then? For our y's and our y primes out here, like the initial conditions. Okay, so there's also a different thing going on there. We don't have initial conditions for y double prime. So in theory, that should just be y and y prime. Or s, y, and y prime. And in this case, it is 0, so that's at least nice. Yeah, that's fine. Alright, so s, y double prime plus 7s y prime plus 6y equals 1? Or minus 1 equals 0, whichever way we feel like writing it. I mean, that could that could work, I suppose. Oh, so we have to do another Laplace transform? Second layer? Wait, where'd that table go? It says there was a table right here. T to the first power. That is not where the table is. Grr. There we go. Oh, there it is. Yeah, okay. I found it, so. I knew that I had this somewhere, right? Like, there we go. So yeah, actually, right? That means that this whole thing here was supposed to be negative. I'm sorry. I missed what that was. So that whole thing was supposed to be negative. So our 3y and our that thing right there. That whole thing was supposed to be negative. I got you. Thanks. Okay, so now just the y's there are not 6y, it's 0. And the 7 is now a 1 sy prime. Right, so this is a reduction of order. So we assume that this is going to be an s squared u prime plus s u equals 1, where u is equal to y prime. We could also, in theory, yes, we could. We could also take this and say, okay, our integration factor is going to be 1 over s. And then this stuff, this is actually not that bad. This is going to be SU prime equals 1 over S. So then, take integrals. Yeah. It's not going to be great, but... so this is going to be SU is equal to, here, this is the natural log of S. A. Absolute value, I guess. And let's have that be over there. We're trying to solve for u in the first place. Okay, fine. We'll have it on the other side. We could just make that the natural log of a constant, so that could come inside and be the natural log of CS times 1 over S is equal to U. And that is going to be equal to Y prime. Okay, let's not bother with that then. Just have the constant be out over that one. It's not over that one. Sorry. That's a 1. All right, then it's plus. Nope. That is why we select from the bottom. Plus C over S. Okay. So y is going to be integral of all this stuff, which, yes, is gross, but it's doable at least. 1 over S natural log S ds plus integral C over S ds. All right, integration by parts. Yep. No. Oh. Integration by parts does not really work there. That's a good question. If we try to do integration by parts one way, right? If we treat natural log as the thing which needs to be derived, we get 1 over S, but then we have to treat the 1 over S as the thing which needs to be integrated, and so we get natural log. So literally we end up back where we started. Actually, wait. That's weird, but hang on. Right? So if we do integration 1 over S natural log S ds, right? We say that this is U, this is V. It doesn't actually, wait, no. Say that this is U and dV includes 1 over S, as well as the ds. Right? Then this is equal to UV. So integrating our 1 over s ds, we get a natural log squared of s. Okay, I regret that immediately. Minus integral of v du is natural log s du is 1 over s ds, which is the same as what's on the other side. So the integral of 1 over s natural log s ds is 2 of those is equal to natural log squared of s. Yeah, it's real gross. 1/2 natural log of s parentheses squared is going to be equal to first part of y. So we get u times v. And so the integral of 1 over s ds is natural log of s times u, which is natural log of s, so natural log squared. And then we would get a plus from the other part. From the other part, we would just have a c natural log s plus c2. Yeah, I think that's gross. So if we go the other way, can we integrate natural log? Wait. Yeah, you're right. Can we integrate natural log? Right? There's no natural log in the Laplacian table. Like, how dare? Right? Yeah, I don't think so. Because natural log is not simplifiable into something that is e to a power. In a way, we already do, right? We've got a polynomial of logs. So whatever the inverse Laplacian is of a natural log. Just out of curiosity. Ooh. I found one. Inverse Laplace transform of a natural log. No, never mind. Oh, natural log of 1 plus 1 over s squared. So that actually makes sense that that would actually work. I mean, we just poke around into things, right? When f of s is equal to yeah, we're getting like 1 plus 1 over s squared, or okay. Yeah, this is the inverse Laplace of the natural log of 1 plus 1 over s squared. So we're not getting... I'm not sure that that's... Oh, now I'm going to have to find out what that is. Anthropic's AI just bankrupted itself. Interesting. Okay. Okay. Inverse Laplace of just log of s does not exist. The person who did this did complex analysis, attempted to do the inverse Laplace by residues and branch cuts in the real or complex analysis stuff, and it ended up failing. So it doesn't actually work. So there's something else that's going on here that just isn't going to make this side end up working out okay. What's a straight integral? It's been so long. X natural log x minus x. So that runs into the exact problem of it's going to be x natural log x. So it's just straight up not going to work. So it seems like this particular problem does not work with Laplace transforms specifically. And this may be why we only did Laplace transforms with constant coefficients rather than with variable coefficients. Apart from just being really gross and messy. But that's good. We learned something, right? So Laplace transforms always work when they're not around particular singular points. But the problem here is that like the Laplace transform is going to create a natural log in it. And so the natural log has a singular point. All right. I think we're going to call it a night here. Thank you so much, Kills It Out, because this has been a good exercise. But it is getting on 1 o'clock in the morning, so. In the next couple of days, I may end up doing we're doing a scientific survey in Elite Dangerous. Specifically, we're going to a particular sector of the galaxy, and what we do is we go up about 1,000 light years, and we go down about 1,000 light years from where our ship is, or where the carrier is, and we try to count how many stars are within the 20 light year sensor range that we have. So we go up by 50 light years at a time. So there are 20 jumps to get all the way to 1,000 light years. Yeah. And we'll keep looking at the numbers of stars that we can see within 20 light years at this place, at this place, at this place, go all the way up to 1,000 light years up, and then go down 1,000 light years again, recording every 50 light years how many stars are within 20 light years of whatever system we jump to. And they compile all of this information from all of the different pilots who are taking ever so slightly different routes. We may end up hitting the exact same, a couple of the exact same systems, but honestly, we don't hit that many. So it's been really interesting so far. Let's see, I got it open somewhere. Right here. So in the... Oi. You punks. But why? ¿Por qué? What are you doing? There we go. So in the Blaprau sector, we have all these individual systems that we've jumped to. Collected the sample at each of these 50 light year marks. We went down on this one, and in each of the systems we had a certain count, and then the max distance away was, how many systems we could see within 20. This is the furthest one away we can see. If in the case of, there are a total of 49 possible systems that you can get in your list before it maxes out. If your list hits 49 systems and the furthest one away is only 8.5 light years, then that means that there are a lot more. And so it produces our density scan is going to be a lot higher in the density region. So here what we've got is a kind of more or less, this is a cross-section of the galaxy. Yes, it's in Elite Dangerous, and yes, it's not a real galaxy, but it is modeled after our actual data that we see in the Milky Way galaxy and also in other neighboring galaxies. So it's just really cool. So this scientific survey we're doing is trying to show what the density of stars in the Elite Dangerous galaxy, which is again modeled after the Milky Way using real science, is going to give us. So we get something like this, and each of the pops that go up really high are the bands of stars in the galaxy. So it's really cool. I will be back, like I said, on Friday, probably doing probably doing Against the Storm, which is our for the long game that we're doing. It is a city building roguelite. Came out in 2013, I think it was. I like it. It's kind of fun. It itches like all of the right little parts of my brain that like that sort of thing. So it's pretty wild. And we may continue our scientific survey if we have done other stuff within Elite Dangerous. Maybe we'll complete like 1 or 2 settlements in against the storm. Then we'll see how that goes. I am UTC. So you are Central. I am +6. Yeah, so the information from the galaxy is, or the Elite Dangerous Galaxy was created by Dr. K. Ross, who is also a Twitch user and a former member of the Frontier Developments science team. Frontier Developments is the dev team that made Elite Dangerous. Yeah, thanks. So she has since left Frontier Development, FDev, but is still doing like sciencey type stuff. So, but a lot of people are very thankful to Dr. K. Ross for creating the galaxy for us. It's really cool. Anyway, hope you all have a good rest of your day and rest of your week. I'm going to, I think, probably finally sit down and raid out to who we got. Oof. Levan's been on for a long time. Noob Tunes is on playing Bloodborne. She's probably signing off soon, though. Let's see. Ooh, Colette. Colette is playing Hades 2. She is one of our friends from Outer Wilds. So she's doing some awesome stuff there on Hades 2. We met her like, I don't know, years ago. So hope you all have a good couple of days. I'll see you later. And we'll catch you next time. So nice to meet you, everybody. And we'll see you soon. My name's Obi-Wan Pez. This is Ensign Pachinko. We'll see ya.